Okay, so Ralph's going to take the last day for us.
All right, well, very good. Yeah, thanks everybody for being here. And our next speaker really doesn't need any introduction. He's one of the co-chairs, so our presentation is by Robert Scheichl. The title is Multilevel Monte Carlo Method. So I turn it over to you.
Thank you. So yeah, I was very happy to be asked in the first workshop to already showcase this, and I'm trying to keep it as low level as possible to give the idea to people that maybe are not familiar with it, hopefully to some of the statisticians. So this is joint work with several people, Aretha Teckentrup and Julia Charrier. Julia is here, who did a lot of the groundwork together with me. Obviously Mike Giles, who is the person that popularized and to some extent invented Multilevel Monte Carlo, Andrew Cliff. And then the latter work, which is more related to what statisticians might find of interest, on Bayesian inference with multilevel methods with Tim Dodwell, Gianluca De Tommaso, and Tiangang Sui. So I'll give a motivation on the basis of a model problem that we've seen now several times. So this will be fairly simple for you to grasp. It's again the elliptic diffusion problem in the subsurface. I will focus in the first part to really get the idea across. What is the idea of the multi-level method, and what's the basic complexity theorem that we can prove for it? And then I'll briefly give you some ideas of extensions and applications. I've got a list that I compiled last night at 1 o'clock of references that you can look at, and a whole web page with further references. The heart of the talk will be the multi-level MCMC, and in particular one version that I have worked on doing multi-level for Bayesian inference. And then I will give, for the ones that maybe have heard me talk on this too often, a little bit of a teaser. You stay in the room, maybe you hear something new at the end with using adaptivity, spatial adaptivity, that is. Okay, so here is the motivation. You've got input with defects, say, for example, here this is a composite material used to build an airplane wing, and at the corner of the material in the manufacture you create wrinkles. Okay, the manufacturers of this always want me to tell you this is not what they do. This was artificially made as bad as this, so they're not that bad normally. These go into modern aircraft as the spars of wings, the front here, and then you want to do an analysis of this and an uncertainty quantification, certification that you dare to fly it and don't want to crash, basically. The example that will be the running example, which I worked on in the context of radioactive waste disposal on the ground, is subsurface flow. So there often the permeability, which is uncertain, gets modeled by a Gaussian random field. You can also work with other ones. We're not wedded to that, but I will focus mainly on that today. You then have a repository. You assume a leakage in the future, and you want to know how long it takes for that to seep out into your groundwater. And then this is what the regulator wants to see. They want to know, this is log time on the base 10, what happens in 10,000 years, and the probability of something seeping out in 10,000 years has to be small. So you want to have certain confidence on this value down here, say. So here is the mathematical or the schematic of what we're trying to do. And I will be in the camp of what we've heard yesterday already, the infinite dimensional world, where we first think of what we have to do infinite dimensionally and then discretize. So in the model that we are interested in, which is a PDE, we have typically an infinite dimensional noise process. So X would be an infinite dimensional setting. You stick it through your model, which would be a PDE, to get the state process. So let me put the second thing up, or what in statistics often might be called a latent field. And this latent field is again in typically an infinite dimensional space V. And then for the regulator, as I've showed you in the last slide, you might only be interested in one quantity of interest, which might be this time it takes to seep out the travel time. So this might be a scalar quantity or a small vector. And you want to do statistics of that. And by Q being a nonlinear functional of U, I want to encapsulate also things like second moments, third moments, or exceedance probabilities. So this would be then a statistic. For simplicity, you can think of the mean of a quantity of interest. So the original origin of the Multilevel Monte Carlo was described in STEs, especially for finance. In that case, Z would be your driving Brownian motion or Levy process. Z would be the Brownian motion or the noise process. U would be your state, the process that you're simulating, like the price, the option price at time t. And Q would be a functional. It could be at the end time, or it could be an integral along the whole path. In UQ, the typical example is that Z is spatial noise process, could be a spatial temporal. Then the U would be your model state, for example, your PDE solution or your model solution. And Q would be a nonlinear, typically nonlinear functional of U. So there's many applications where this kind of paradigm is also present and where Multilevel Monte Carlo also works in imaging, biological chemical reaction networks, interacting particle systems, to name a few. The inherent problem I'm addressing is that even though I'm only interested in a single random variable Q, and I could just say what is the distribution of Q, it is often only known or describable via the distribution of the latent field, which is high or infinite dimensional. So here is the basic idea. In a practical implementation, we've heard a few talks on this. You'd, of course, not work with the infinite dimensional problem. You cannot put an infinite dimensional problem, except in special cases, on a computer, so you would discretize. You would discretize your noise process. We've heard about Kahn and Löw expansion. There's many other ways of doing this. So the Z will become a ZL. L is now my sort of level parameter for the discretization. I then have a model of fidelity L, or of approximation property L, which gives me a solution, PDE, approximation of the PDE solution in a space VL, which could be a finite element space. And then in the output calculation, the integral might have to be done with quadrature as well, so you might have an approximation in this functional too. And finally, and most importantly, we cannot typically work out expected values explicitly, so we need to do quadrature in order to work out the expected value. And this is where most of the talk will be about. So in the context of my examples, here for the SD, the level would be related to the step size in your time stepping. Z would be your Brownian increments. That would be now Gaussians with a certain variance given by the step size. And UL would now be a discrete set of values of your approximation at times Tj, for example, on a uniform grid. In the UQ example, you'd have, for example, ZL now being the coefficients of your KL expansion of Z, and UL being the coefficients of your finite element solution. There is many other approximations you can do, and that I will not have time to talk about. You could do the level hierarchy could be related to P refinement, so that is means we're talking about higher and higher order polynomials. That would be a spectral Galerkin method or an HP finite element method. You could use model order reduction to get yourself coarser models. You could coarse grain in particle systems, etc., etc. What I'm going to use, or what is being used in the analysis or in the justification for the gains with this methodology that I'm describing, is that we're assuming a certain hierarchy. We're assuming that we actually can control with L how accurate we are making the approximation, and for simplicity, you can just write it as a power of 2. So we're assuming a certain exponential decay with L in my bias error. So this would be the bias error. But typically, and I think most of you will be familiar with this, the cost will grow proportionally or most likely gamma will actually be even bigger than alpha. So you will actually get a cost growth corresponding to the decrease in the bias error. And so I want to assume these two to describe what I'm going to use as an acceleration technique now to solve this. So here is my model problem that we've seen before. I'm going to just focus on the case where we've got log normal. So I'm going to assume that my diffusion coefficient is always in the form e to the power z, where z will be a Gaussian. So this is the PDE. A typical model problem is where we have got flow through a cell. So you've got a pressure gradient across the cell, no flow on the top and bottom. The V space, the infinite dimensional space for the latent field would in that case be the H1 sub F space that we've heard about. The space Z for the field up here would be L infinity, or you could take something a little bit more smooth in the long run, but at least it has to be L infinity. And then as an example, as the running example in my talk, I will take the rougher of the two that Julia talked about in her talk, namely the exponential covariance, but everything could be done with the Gaussian covariance too. So this is whether you've got a square here or not. And it was described very carefully by Julia, and mathematically there's quite a huge difference between those. Also, Tony O'Hagan mentioned that yesterday. So now I'm parameterizing my field in some form. This could be a Cowan-Löw expansion. What I use mostly is circulant embedding and then FFT, which you can interpret as a discrete KL expansion in some sense. In which case, now I'm talking about IID parameters that are all N01. But SL typically will be large. For space, I'm going to discretize V by, I'm not going to go into much detail, but I think it's not crucial that you understand more than what people have already said in this conference. I'm thinking about discretizing this PDE. So it's written here in weak form. Max described roughly how this is done. And then I'm saying instead of satisfying this variational equation for all functions v in my H1 space, I'm only satisfying it for a subset which consists of continuous piecewise linears. So they are linear on each element of a mesh, and the mesh is typically a triangular mesh. So on each triangle you have to think of a function being linear, and it's continuous across the edges of the triangles. And again, here we've got a sort of a geometrically decreasing sequence of mesh sizes. So from a point of view of computation on the computer, again, there was 2 talks on this. All you have to do in the end is solve a linear equation system. So there's a matrix now which depends on my random field. So because the coefficients entering this matrix here will be omega dependent, will depend on the randomness, and hence the solution will also. And ML and SL, which are the dimension parameters here, are both huge or big. So here is a pictorial view. This is our XL space. So we've got Fourier mode. So if I truncate earlier with my Fourier series, I get smoother fields, not representing all the variability. This is actually the same field just truncated earlier, the same realization of the field truncated earlier, and then adding more and more components. And this is the spatial hierarchy. So this is a coarse grid, this is the finer one, etc., until the finest. For this particular model problem, going back to my 2 assumptions, it turns out, and this is very specific to the exponential covariance, that alpha is 1 and gamma can be made 2 if we use an efficient solver, an algebraic multigrid solver. Okay, so here is Monte Carlo, and what's the problem? If I want to average work out EQ, I can just take samples from my model, IID samples, or rather I take samples from my coefficient, feed them through the model, and work out my quantity of interest, and then I'll just do an averaging. What's the problem? the problem is that there is obviously two error components, which can be very easily analyzed if we take mean square error as our measure. So this is my estimator up here. This is the quantity I'm actually interested in with Q without an L. And the mean square error can be easily seen to expand into a sampling error term, which is the typical variance divided by number of samples, plus a bias term or a square bias term here. And because there's a sum here, you can very clearly see that I need to both make n large and get the bias error small. So, for example, remembering our assumption on the bias error, which decays with 2 to the minus alpha L, and the cost which grows with 2 to the gamma L, this means that my L, in order to get this total error below epsilon squared, these two conditions imply that I need to choose my L, my capital L, to grow logarithmically with epsilon to the minus 1, but also to grow proportionate to alpha to the minus 1. There's a gamma missing. Okay. No, correct. This is just to get the bias error, sorry. This is just to get the bias error below the tolerance of epsilon squared. To get the sampling error below the tolerance of epsilon squared, we just need to pick n to be proportional to epsilon squared. Now, the cost for each sample, remember, is 2 to the gamma L. So if we multiply the cost of each sample times the number of samples, this is the cost you get. And in the model example, this means if I want to reduce my error by a factor 2, I need to do 16 times more work. And this very quickly gets out of hand. And I haven't even included the numerics to show it. Okay, so here is the multi-level idea. It's basically been popularized by Mike Giles, even though it has been already written down 10 years earlier, but nobody actually discovered it. So it's just simply saying we are introducing control variates. So we are taking our process, we can write this collapsing sum down. This is just an equality. And we, instead of working out the expected value of QL, we do it via subtracting as what you can think as a statistician as a control variate. And we're doing this in a systematic and hierarchical way, in such a way that each of these terms will turn out to be cheap to compute, or cheaper to compute than the left-hand side. So I'm going to do Monte Carlo in the simplest case on each of the terms. But, of course, I'm going to pick different numbers of samples for each of those Monte Carlo estimators, and that's what's crucial. So Y will always denote my difference between Q's on 2 consecutive levels. And very importantly, which is maybe hidden a little bit in this mathematical notation here, when I'm doing a sample of YL, it's very crucial, and this is actually the heart of the whole multi-level, that these two come from the same sample. And the stronger you can couple those two, the stronger you can link the samples from this with the samples from that, the better variance reduction you're going to get. So, very trivial observation is that if QL converges, as I've assumed, then obviously a convergent sequence is also a Cauchy sequence. Obviously, the variance of the difference has to go to 0. How fast it goes to 0 will be crucial for the efficiency of the method. But in principle, and in many situations, in the best case, as we go finer and finer, at some point we only need order 1 samples on the finer levels. Now think about what I've told you before. We're doing a complicated, I gave you a 2D example. You might have a 3D simulation. If I'm doing a 3D simulation on a grid with on level 5 versus on level 0, that is 8 to the power 5 more degrees of freedom. And even in the best case where you've got an optimal solver, a lot more work. So if I only need to do one of those expensive samples, then I win a lot. On the other end of the spectrum, on the 0th level, I'm not getting away with a free lunch here. I still have to do Monte Carlo. So I still have to do as many samples as before, but now I'm gaining from having each sample being cheap. So my coarsest model, I'm going to choose a very coarse one, And I guess in this conference we could discuss also using emulators. You can use something, whatever you want as your coarsest model to be very cheap, and on that one you're going to do lots and lots of samples at almost no cost. And then you can optimize the NLs, which I'm not going to talk in detail. There's some maths how you can balance the NLs so that the middle levels are never worse than the end points. Okay? You can prove this. You can assume a decay rate on your variance difference, the difference of variance of the difference, and then you can rigorously prove. So in the case of the ST, this was done in the original paper. In the case of the general case, this was done in this paper, and actually the even more general case where we're not only looking at Monte Carlo but also quasi-Monte Carlo and stochastic allocation was done in Aretha's thesis first. And so this is the gain you get. If you look at this number here, we had 2 minus gamma over alpha. So in the best case, I'm down to the Monte Carlo rate, epsilon to minus 2. And but even in the worst case, or in the case where the samples on the finest levels dominate, I'm get a gain of beta over alpha. Now beta is the rate of the variance, which is a square quantity, and alpha is the rate of the bias, which is linear, is first order. So this is typically also 2. So typically we gain 2 powers in our cost. So here is the example. For the running example, again, smooth functionals, exponential covariance, alpha is 1, beta is about 2, gamma is about 2 with algebraic multigrid. So instead of having sum of 2 and gamma over alpha, we get max of gamma, 2 and gamma over alpha. Or in other words, instead of having n times m, we get max of n and m. Okay? So this is why instead of epsilon to the minus 4, we get epsilon to the minus 2. And when I say asymptotic cost, when I talk about optimality here, then I say in the regime that these rough fields, where the gamma over alpha is the dominant part, especially in 3D, we have an optimal uncertainty quantification method, because in the I can't get away with solving a problem to a certain accuracy if I don't do at least one solve to the required accuracy. And here we're talking about in the case where the fine grid solve dominates, I'm essentially up to the constant getting the same cost as one solve. Okay. So here is just some numerical evidence. Here you see that for each particular choice of your tolerance, you have a sequence of NLs. So you see that on the coarsest level, we do lots of samples, 10 to the 6, this says here. And then as we go down, on all the methods, on the coarsest level, we do in the order of 10 to a few tens of samples. And here is the cost scaled by epsilon squared. So as I said, the standard Monte Carlo grows like epsilon to the minus 4, whereas the multilevel Monte Carlo is flat here, so it grows like epsilon to the minus 2. Okay, so a little bit of comments. First of all, a lot of this can be proved, and in fact, the theoretical results in Julia Sharia's talk earlier are almost proving everything we need. We have already got everything in that. If you look at those slides and relate it to my assumptions, you will see that that proves them. But what I really want to focus on here is that you don't just get a nice mathematical result, you actually get real practical gains. Even for 2 levels, you will already get huge gains. And not just asymptotically with epsilon going to 0. The models do not have to be nested because we're only subtracting quantities of interest, functionals of something. So I could take a finite element calculation and couple it with an MD calculation. As I said earlier, I could use an emulator and couple it with a finite element calculation. You could do multi-scale methods, we've heard about that. You can do model order reduction, you can do low-rank tensors, we've heard about that. And you can do different quadratures. And so, so this is the colored ones are ones that I've worked on. I will have a little slide on multi-level quasi-Monte Carlo just to show you that quasi-Monte Carlo and multi-level can be complementary and can really work well together. It's not restricted to differential equations. I've started to work with physicists and chemists to use it in their applications of Markov chain Monte Carlo methods and Monte Carlo methods, and it can be used for integral differential equations like neutron transport. But at the heart, and I've hinted at it before, is that you need to couple levels well. If you do not get this coupling, so take for example a wave equation and go to fairly coarse meshes, as anybody knows, if I coarsen too much, I will just get garbage, and I will get very different shifted solutions. If I then want to do point evaluations and they're phase shifted, you're going to get very big differences here. But the coarser levels in my algorithm, they are artificial. They're not physical. So what I always say to people that come to me and say, can I use it for wave equations, can I use it for time-dependent problems, is that if you put a lot of dispersion on the coarser levels, I think it might work. But of course, that the proof is the proof of the pudding is in the eating. So there is a web page where a lot of, essentially up to a certain point, every paper was listed. I think it's not true anymore on Multilevel Monte Carlo, because there's just too many now. Here is just one plot to show that QMC can be complementary. So we're restricted by the epsilon to the -2 of the Monte Carlo for my multilevel Monte Carlo, and this is what we see here in this plot as well. So the multilevel Monte Carlo, the red curve, is again restricted by 2 for this same problem, just a smoother Matern parameter here. But if I use quasi-Monte Carlo, which is not restricted by epsilon to the -2, which can converge as 1 over n, you actually can achieve that. You can get an order 1 method, epsilon to the -1 cost growth. And this is not restricted to PDEs or to this model problem. Here is neutron transport, and you get exactly the same picture for neutron transport. Okay, so let me come to the probably more interesting thing for the audience here. So now I have the same paradigm. I have my model, I have my parameter, I have my model and my output, and I want to do statistics. But now I want to condition this on data, y-ops, on observed data. So my statistics at the end will be done with respect to posterior and not with respect to the prior on Z. Okay? So first a little literature review, and then I'll give you an example, and then I'll describe my own work here in this paper in detail. So the first paper is actually by Andrew here in the audience with Chris Schwab and Viet-Ha Huang, where they did a version. There's many versions, so I will only describe one version. Then we did this work. There's been lots of activity since, in particular involving Cody Law, Colin Cotta and Alistair Gregory, and of course Raul Tempone as well. And then in the meantime, the sequential Monte Carlo mafia have taken it on, and they have written tons of papers on it. So there is various versions and guises of this. So the gains are similar, and I hope I can convince you in the next few slides. But it's much more difficult to ensure consistency, that you've got this collapsing sum hold, plus variance reduction. So it's pretty easy to get one of them working and the other one failing. But obviously if we have no consistency, as I call it, the collapsing sum property, then if I go too far with my fine level from the coarse level, I will never get away from that bias error on the coarser levels, and that would be essentially not convergent, as I want, not consistent. On the other hand, if I try very hard to couple, to get rid of this consistency problem, then I often ruin my variance reduction properties. So okay, now this slide, I tried to I think many of the speakers before me had the same problem. It's like, how do you get everything into a few slides? So I hope this is understandable enough, especially in the context of what we've already heard. So we are looking at a posterior distribution of our ZL. Remember, my ZL was my parameters in my KL expansion, say. And I'm conditioning that on the observed data, but because I'm conditioning with respect to a model that I'm only evaluating inaccurately, my posterior will also be L dependent. And the L dependence comes out of this. I mean, of course, also of ZL, but it comes in particular out of my response functional FL being itself a numerical approximation of the response, of the model response. So here I'm assuming an additive Gaussian noise on my measurements. So this would be the likelihood here with a certain correlation on the data. And then my original prior that I had put on before already in my previous slides. And so now I want to simulate, or I want to work out statistics with respect to this distribution. So what were the key ingredients in my multi-level? I had the telescoping sum. So this was the first key ingredient. I had, very crucially, that the coarser model is obviously cheaper than the finer, otherwise I'm not going to get any gains. And I had this variance reduction, so that the difference between two consecutive levels, the variance, goes to 0, and so I can get away with much, much fewer samples on the finer levels. In MCMC, as I tried to highlight already up here, we don't have that luxury to just simply put this collapsing sum down, because the pi itself depends on L. So I kind of have to split the two expected values here, because one is with respect to pi L minus 1, one is with respect to pi L. So I believe in Andrew's method this is corrected. So they formulate it as an expected value under one of the two, and then you work out what the correction has to be, or the weighting has to be on the other one. We are looking at it exactly like this. So you actually look at the two separate expected values, but remembering that in the end of the day, when I do Monte Carlo, all I'm doing is summing samples. So I'm just doing a sum over some samples. So I can just make sure that the samples I am summing over here and the samples I am summing over here are strongly correlated, are linked again. These are, again, have to be samples that strongly coupled so that I can expect this variance reduction here. So here, I'm not doing anything magic. Here I'm using your favorite, or you can use your favorite MCMC that you want to use on the coarsest level. Here, I'm going to describe to you what I'm doing for this two-level coupled Monte Carlo estimator. And then, of course, I can do that on every level. So I only need to describe it for one level. What I'm going to simplify to, just for sake of the time I have, is I'm now going to fix the number of modes, the number of parameters on each level. In the analysis in the paper, we also, and we use, crucially, that on the coarser levels, we can use fewer parameters than on the finer levels. And we bring them in the same way as in a reversible jump a la Peter Green. You can add more and more the parameters as you go along. But the talk today, I'm just going to fix the parameters. And I'm just going to focus on the spatial discretization. So just as a recall, I think we've seen it, but just I wanted to put it up. MCMC, Metropolis Hastings, for the people that are not familiar with, starts with a state, typically burned in. Typically, you have already run this thing for a while. Then you propose another state, a next possible parameter, a next parameter, according to a certain distribution. And this distribution should be well chosen, in particular in high dimensions prior reversible. And then you accept this x prime if with a probability alpha that's given by this Metropolis Hastings ratio. And you get the likelihood from, or the posterior distribution from the x prime and the posterior distribution from the xn. And because they're divided, the normalizing factor is irrelevant. And you have to know what the probability of jumping to the new place is and what the probability of jumping in the reverse direction is. It produces a Markov chain if you satisfy the right properties with Q. and you can do inference in the same way as we did before with IID samples. So even though the samples are not IID, I can just average and I get a correct estimate for my expected value under the posterior. And so this is a very commonly used technique, sometimes called the gold standard, because we know that the distribution converges to the correct distribution. So here is the multi-level version. So I don't know, I think this is very badly visible. I always struggled the last few days. But basically I'm gonna have on level 0 a bunch of proposals. Well, not a bunch of proposals, a bunch of states. So I'm gonna run my coarsest chain to produce proposals or states Z L0n. Okay. Now this is the first level. Then on the next level, I'm gonna pick with a certain subsampling rate. I'm gonna pick states in this chain as proposals that I'm gonna propose down here. So let's assume the first one is, that's where I start, is used. Now I'm proposing this as my x prime on level 1. And it's actually easy to work out. Well, actually, I shouldn't say it's easy to work out. We got it wrong twice to prove it. But the acceptance probability or the transition probability for this, from moving from one state to the other, is in fact, or the ratio of the two is in fact proportional to the ratio of the posterior distributions on the coarse level, because we know that the coarse chain converges to the coarse posterior. So this is actually a surrogate transition, a special case of a surrogate transition method, already described in Liu's book in 2001. And basically you can prove that the correct transition probability, or the ratio, is the ratio of the coarse probabilities, coarse posteriors. So now I know how to compute this acceptance rate, so I accept or reject, and I move along. Then I go to level 2, and I subsample maybe every second one here, and I make proposals further down. And that's how I hierarchically build my chains until I'm at L and L minus 1, and then I use those in my inference. Okay? So here is a little bit of bookkeeping of the various subsampling rates, but in essence you just get, after having gone through L levels, you get your 2 chains. Okay? Each of is a Metropolis Hastings in each level. I'm doing a Metropolis Hastings accept reject step, so it is a Metropolis Hastings, so each of them converges to pi k. So in particular, this means that my multi-level method is consistent, because I'm adding and subtracting. I'm doing it with different proposal distributions on the different levels, but well, I'm getting to every level in the same way from 0 up to the L minus first to the L. So there's no bias between levels, but I obviously have occasionally a rejection here. So occasionally I will not accept one that I've proposed, in which case my 2 proposals or my 2 states at level L and L minus 1 will differ. So you're in 2 different places in the parameter space, so there's no reason why the variance of the difference should be small, but it's at least bounded. And the nice thing is that, as you can imagine, if I make my model finer and finer and finer, I will eventually accept everything, because I'm essentially sampling from the same model. They're converging to each other. And this can be proved. So the 2 main theoretical results in our paper were that 1 minus alpha L is actually bounded by order, depending, again, this depends on the spatial and on the parameter regularity. In the exponential covariance case, it only grows with order h. In the Gaussian case, it would grow with order h squared. And therefore, the variance reduction also is guaranteed and can be bounded rigorously with a certain rate. Okay, now a few links to the statistics literature. So first of all, there was a lot of confusion between our final paper and the earlier preprint. In the earlier preprint, we didn't do the subsampling. In the final paper, we do the subsampling. So my answer is, it's fine. The algorithm without subsampling is fine, but the subsampling is extremely useful. There's two aspects of MCMC that make the final chain correlated. One is how correlated your initial proposals are, and two, how often you accept and reject. If I start with better or with more independent proposals coming up from the coarser levels where they're cheap, then up here I'm going to have much less correlated samples, and that will be helpful of doing fewer samples on the final levels again. As I said, it's a special case of the surrogate transition method described already in Liu's book, which actually, once I was told about this book, I find this a treasure trove. I'm going to have a few days where I sit down and read this book, because essentially everything I've heard before from people I've found in that book mentioned as well. So the version I knew about was delayed acceptance Metropolis Hastings, which is by Andres Christen and Colin Fox, and this has also had some attention. Christian Robert has worked on that recently. But crucially, and this is the difference between this literature, nobody has combined it with the variance reduction idea, so with the differencing, and or proved any rates. Here is an example. It's our usual example, although here we've used the separable exponential, which is the one norm in essence on the, which is a bit stripy, as you can see, but for the purposes of my demonstration, it's fine. I'm using here in this example synthetic data, so I'm taking one sample as my truth. I'm measuring 16 points with that assumed measurement noise, and I get here an example of my posterior samples on the finest level. You get the same decay of the number of samples you're using, although the constant seems a little bit higher here. It's in the hundreds rather than in the tens. And you see the same growth or the same difference in the growth of cost versus accuracy. When Monte Carlo is epsilon to minus 2, Multilevel Monte Carlo is epsilon to minus 4. Our proofs only prove epsilon to minus 3 for multi-level, but I think it's more like a problem with our proof technique. Here we've changed the modes, the KL modes, from the coarsest to the finest, from 50 to 150. And here is an important picture. So with the subsampling, we're subsampling very generously here. We don't need to, but in this example, we subsampled with the estimated integrated autocorrelation time as the sampling rate. This is the real integrated autocorrelation time on level 0 from a PCN random walk for this example. So this is a prior reversible random walk. And this gives us this integrated autocorrelation time. By subsampling this and screening, using this surrogate transition, like moving it up, we get immediately already 3.66 autocorrelation time on level 1. So we almost, or we're very close to uncorrelated chain, and it goes close to 1 at the end. So this is why, remember, this is 1,000 times more expensive than this, 4 to the power 5. So if I can get away with no throwing away of samples because I've got an integrated autocorrelation time of 1, I'm gaining a huge amount. So far, what I've described was all for this PCN random walk, which is dimension independent, but doesn't use any gradient or Hessian information, but you can use any other proposals that you want. And in particular, we've been working on DILI, this dimension independent likelihood informed one, which uses a low rank Hessian approximation at a few points. And so this is unfortunately very, very preliminary results, and I'm not completely happy with them. I got them literally at 8 o'clock this morning from my student. So you see the gains in the integrated articulation time here, but I'm not quite sure whether his estimates, he's not has had time to have too many samples, because my predictions would be that these should be much closer, because we're not doing anything different on the finer levels. We're just using a different proposal on the coarsest level. This is a harder problem. That's why the integrated articulation time is higher. First of all, we are sampling at 36 points and not at 16. We have got this as our truth, and we've got also a more complicated source term. And we're working now on doing multi-level DILI, so really doing a multi-level hierarchical low-rank approximation. Okay, so I see that I have about a few minutes. Let me just quickly zoom past some ideas what I think needs to be done next, or what I'm doing at least next. In these aerospace applications, the defects or the randomness is typically localized. So we've had this random field, this Gaussian random field. So if you take different samples, you need to get more accuracy, you need to refine almost everywhere. But if you have these wrinkle defects, you only really need to refine near here. Equally, if your source term or your quantity of interest in the subsurface problem is localized, if you don't know where something is leaking, then you also would like to only refine your grid around there. So I want to use sample-dependent model hierarchies. So back to our model problem, but now think of VL as being omega dependent. So for each VL, for each omega, and for each L, we build a specific TL omega with a specific HL omega and a specific size of the matrix system. And we can control, for example, how we pick these by an error estimator. There's a lot of literature on a posterior error estimation in the finite element literature. So we're picking our levels adaptively. So here is an example. Here is this streaky Gaussian random field with now we're assuming that here is where the source term leaks in. In another realization, it might be down here. In another realization, it might be up here. Here is down here, I think, is where the output functional is evaluated, and here is our mesh. So this was first used, or adaptivity was first used by these guys in Multilevel Monte Carlo. The most interesting paper to read, I would recommend, is Evgenia, who is here's paper on this, which is much more in the spirit of what I'll describe quickly now. So one thing I want to describe quickly now is what I mean by continuous level Monte Carlo and why I think it is very exciting or interesting paradigm to use. So this was our multilevel Monte Carlo expansion. I want to free, in some sense, the level parameter from being integer. So L is an integer here. I've got a 1 artificially here. So what I'm doing is, instead of having a sum, I'm going to go to an integral. Instead of a collapsing sum, I'm going to do fundamental theorem of calculus. Okay? So L, my level parameter, is now a continuum. And I'm assuming that Q has certain mild assumptions so that I can differentiate. And then I can write down formally a Monte Carlo estimator of this type, where each of these integrands is itself a Monte Carlo estimator of derivatives. And we can prove the same complexity theorem as for MLMC for this. But we can actually do better. We can choose, or we can interpret QL as a stochastic process, and we can let L up here be a stopping time, which is a random variable independent of Q with finite expectations. And then, due to Dinkin's formula, or it is still in some sense fundamental theorem of calculus, you have the same result here. And for what will become apparent from practical purposes, we're going to put an upper bound, an L max in there, so that, we're essentially stopping this if it's bigger than L max. Then I can write down a continuous level estimator in the same way as written down before, but now taking into account that L is a process, a stopping time, and has a certain probability, so I can write down this estimator and note that the n is now outside. I'm doing 1 on n, some 1 I equals 1 to n. So you might ask yourself, where's my gains, my multi-level gains? I'll explain in a minute. In particular, well, maybe I'll say it now. Oops. In particular, because I'm going to make L, this stopping time, an exponential distribution, most of my samples here will stop close to 0. And so most of the time, my integral will only integrate to very small L, which is why most of the samples are going to be cheap. Only very few times my exponential will draw a large L, and I will actually have to work out what Q does for very fine fidelities, fine realizations. You can prove, and this is now why I said we can do better. This is related to what Rhee and Glynn proved for MLMC, but I think it's more elegant here. We can see that the estimator is unbiased with respect to the real quantity of interest if I pick L max to be infinity. So this is an unbiased estimator of the real quantity of interest of the infinite dimensional problem. So no bias error. And as I said, we can prove the complexity result. But what I think Rhee and Glynn brushed under the carpet a bit is that you can only prove it for beta bigger than gamma. If my variance decays faster than my cost grows, then I can get the optimal Monte Carlo rate, and I can choose L max infinity, so I can make an unbiased estimator. We have actually proved that if beta is less than gamma, then you do have to pick L max less than infinity, so you cannot construct an unbiased estimator. And it's kind of understandable. If you remember from my first slides on Multilevel Monte Carlo, I had level 0 being dominated by the Monte Carlo error, level L being dominated by the fine element error. If level 0 is the dominant one, then I can essentially hide my bias error under that error. If that one is the dominant error, I just have to solve something on that grid. And I cannot get around doing that. And if I went to infinite L, I would have infinite cost. So it's unbiased, and I've just described what I've written here. We see here that the rate at which the NLs have to decay in some sense is not, you don't have to pick a optimal choice. You can be in the whole range between min of beta and gamma and max beta of gamma. So it's robust in some sense. You don't need to pick the right rate to get the right estimate. And one thing I haven't really said before is, what am I going to do with L? What's my L, my continuum parameter? Well, I'm going to use the error estimator, the log of the error estimator, as my level parameter. So I'm going to get an error estimate for my sample, and I'm going to stick it on that L, or the log of that, on my level. And this is really good for doing adaptive finite elements. So I think I'm running out of time. So here is an example where we have this random pulse on the right-hand side. It's very similar to the model problems we did before. I'm using as the level parameter the log of this error estimator, or the relative error estimator. And the practical algorithm, just to give you a pictorial view, will calculate samples that will fall at some points along this line. In this example, actually, there's not much variability, but in other examples, you could imagine that one sample will have its realizations very differently spaced than others. I interpolate between them, and then I can work out what the practical estimator looks like. So this was a very abstract estimator, but once I've done a linear interpolation or a polynomial interpolation between 2 points, I can actually work out what these weights are. And this is what it does. In 2D, we get some gains because we've got cheaper cost with the adaptive. In 3D, first of all, the uniform grid refinement does not even kick off. It's just too costly. We can't run it on a single processor. And moreover, the uniform is not unbiased, because gamma is actually bigger than beta in the uniform refinement case. So in 3D, the results, unfortunately, are not here yet. I'm expecting huge gains from this. Okay, so finally, I really see a huge potential for this, and I think others do too. I mean, it was already yesterday on the slide as one of the working groups. So I really think this is something we should discuss here, and is of very big interest. there's many open questions, so it's quite exciting for young guys to get into because there's lots to be proved and to be shown and to be done. I know this is a bit controversial. Some people said that to me before, but I really think it's a no-brainer if you have a model hierarchy to use it to actually do this kind of approach. There's many applications to apply it to, and in particular in Bayesian inference and data assimilation, we've only scratched the surface. I think that's it.
Let's open up for questions. Yes.
My apologies if this comes from a lack of caffeine, but I understand what you're doing with when you've got a differential equation for your posterior distribution, but if I was to be doing generic Bayesian inference where I had an incalculable posterior and you said I could use an emulator as my coarse model, what do I use as my interim models for my model hierarchy?
I haven't used it with emulators, but you could build, if you had, I think the emulator example is more difficult to justify because if you put more points in, the cost doesn't grow exponentially. You just get a little bit more cost. So I mean, the only way I could see an emulator work is if you use it on the coarsest level, and then you have your real simulator and various versions of the real simulator, for example, with different grid sizes in your example, different resolutions in your, or other refinements in your simulator as the next levels.
Physical model at different levels of accuracy to gain my...
Yeah. I mean, you could use a level, I mean, in fact, in particular in reduced order models, like where people have used PCA to construct reduced order models, the first thing I saw as a problem when I thought about using multi-level there is that typically the cost to build them is more than to actually sample from them, and the sampling cost only grows very minimally, so there's not much gain there. And I should mention there is a work by Max Gunzburg and others, and Catherine has already alluded to, that is called Multifidelity Monte Carlo, where you just throw the models in and you let the as in our case, you let the estimators that estimate these variances. I didn't really talk about the practical algorithm much. So the practical algorithm would actually estimate variances in order to choose the NLs, the number of samples on each level, on the fly. And in the in this multi-fidelity, people really just let the algorithm deduce what the variances between different models are, and then if you have big differences between models, you will get big savings, like the coarser model being run on most of your samples and defined a very few times. If you don't, it will detect that and it will just give you small gains.
Other questions? Yeah.
Have people thought about a situation when there isn't a hierarchy built in?
I think this fidelity, multi-fidelity. I mean the.
You have to estimate. You don't know the variances, or even the relative fidelity of the models. You have to estimate those.
Mm. But I mean, in all of even in these multi-level ones, we do for very simple model problems know a priori what the rates are, and we can just stick it in. But in practice, you would always estimate them on the fly, and even for models which are clear PDE, clear structure of hierarchy, you would estimate for the practical purposes, especially if you use them with quasi-Monte Carlo, where there's also an aspect of, are you already in the asymptotic regime of your quasi-Monte Carlo? If you just take these a priori rates, you get not very optimal performance. But the good thing about Monte Carlo, which is one of my things that I like about Monte Carlo, is that you have for free, I mean, I guess the statisticians use that all the time, you've got your estimators, your a posteriori estimators for free, because these variance sample estimates, they're just there for you to use to learn about your predictions.
All right, I suspect there's other questions, but I also want to keep us on time, so let's go ahead and hold the other questions until the break. Thank you again.
Yeah. There is 3 pages of references for which I sweated over last night, so I wanted to show them. So,